Right, good evening everybody. My name's Hayden Nuttall and Rob May, and we're here to talk to you today about computational engineering in general, but in particular some of the work that we're doing at BuroHappold. So I don't know how familiar you are with this subject. I guess it's not something that is taught as an actual subject at Imperial. So let's have a few definitions so that we all know what we're talking about. So this is a fairly new and rapidly growing field where people are applying advanced computational techniques to normal engineering practice. It's a different way of doing things. So computational engineers, which could be you, and it's certainly Rob, it's a little bit of me, have extensive knowledge of engineering principles and the science behind the engineering. This has to come first. But in addition to that, if you really want to get under the skin of this field, you need to have good knowledge of maths, algorithms, and computer languages. Now, just a bit of context about why this is important. We spend an awful lot of time doing the engineering these days. Things are becoming very, very complex in the commercial world, and we just need to find better, more efficient ways of doing the work that we already do. It's not a substitute for what we do, it's just a smarter way of working. So we need to improve the quality of what we give to people in order to build what we've designed. There are too many risks in our industry. There's too many people involved, there's too much coordination. We're trying to reduce our risks. We also need to take less time designing elements that are actually quite repetitive. We also are constrained massively by what software can do. And if we wait for the software producers to line everything up and get things to talk to other bits of software in the way we want, we'll be waiting an awful long time. We've been waiting to this point and it still hasn't happened. And the real reason for this is we want to create more time for doing the actual engineering, not the number crunching. We want to take the stuff that can be done by a computer away from the engineer to free them up to think. So a little bit of context first, and I want to play you a video. I'd like to play you a video, and maybe I will in 1 second. Not the right video. Try again. So that video was something that was produced for High Speed 2, which is the new rail link we're going to have between London and Birmingham. And it was produced to illustrate what we will have to do as designers who want to work on that project. This is being mandated by the clients. What the client is saying is that everything is possible now in a digital world, from the start of design to the end of design and beyond. So this isn't a choice, this is reality. Contractors are using it to do virtual erection. They try it out before they actually do it. Cost consultants are using it to look at the costs and the cash flow that the client will have to spend during the project to keep the project going. And at the front end of all of that are the designers. Now we have to help create this building engineering, building information model, the BIM model, in order for it to have a life of its own and be taken over by different people, by the contractor, by the facilities manager. This is a lot of information that we have to create and manipulate and change quite often. And computational engineering is really about enabling us in all aspects of design, but particularly in the aspect of BIM, because that's the world that we're working in now, to be able to create this information and use the information quicker and be able to change it. It also has many other uses, and Rob will show you some cool stuff a little bit later on. So in BuroHappold, we have been doing this kind of work for quite a while now. People like Rob and some of his colleagues were there at the beginning, and near the beginning for us was a project in Macau called, it's been renamed now, called Morpheus Hotel. And this is a project by Zaha Hadid Architects, and this is one of the most complex projects that's ever been built. And I'm going to show you how computational engineering helped us with this project, and I have a few videos. So, another video give you an idea of the complexity of this really astounding project, but the engineering challenges are colossal. Sorry, I'll get the hang of this. What's interesting here is the complexity doesn't stop on the outside. So if you're ever lucky enough to go there, as you walk through into the lobby, this is what you can expect. So what you're seeing now is part of the internal cladding. Now you're going up in the lift, and these are some of those big voids that you can see from the outside. And if you like free diving without coming up for air, you can have a swim in the pool, which is located at the top of the building. So I'll probably stop it there. So before I get into the computational engineering part of it, a little bit about the building. So the structure is about 170 meters high. It's got 2 concrete cores, an exoskeleton, which is, think of a shell on a turtle. It's something that's giving rigidity and strength, and it's placed on the outside where, as you know from your studies, it's the most efficient. But they work together to share lateral loads, and Macau, whilst it's not particularly seismic, has a requirement to design for earthquakes. They also have typhoons there, so a combination of earthquakes and typhoons led us to the evolution of this dual system. So this just goes to illustrate the detail that goes into a BIM model these days. So these are the concrete cores, every opening, every part of it, every foundation, all the concrete elements, and here's the complete structure. Right, initial challenges. When this project came to us, the first thing we had to work out is how are we going to deal with this geometry? This geometry does not obey any kind of maths that you can write down on a piece of paper. It's completely freeform. How are we going to work with that? What influence would that geometry have on manufacturing techniques? Just because you can draw it doesn't mean to say you can make it. And how on earth are we going to connect these members together? If you look at some of these junctions, I'll show you some of the sizes of these members, how they're going to come together. This is literally unprecedented in our industry. How are we going to exchange information within the design team, within BuroHappold? We also did this working from our Hong Kong office and our London office. How on earth were we going to talk to each other about this design and exchange information where we split the design between the offices and we still have to coordinate with other parties who are in various parts of the world? And how on earth are we going to document it? This drawing does not lend itself to, this building doesn't lend itself to drawings. In parts maybe, but not everywhere. How on earth were we going to tell the contractor what we wanted him to build so that he got it in the right place? And it was to the quality that we wanted it, using the materials and sizes that we specified. In amongst all of that, we had a really tight program for the design of this project. The client did not want to wait for 5 years while we worked this out. We committed to a program for delivery, and then we had to work it out. And as I probably said, there were no precedents for building like this. So we needed to work differently. We needed a different approach. So what we did was we worked out what tasks we would have to do at a very high level and what tools we would need in order to make that happen. So it needed to be parametric because we knew the architect was going to change this always. We had to create the geometry in order to do anything. We needed to make sure that bits of structure didn't clash with bits of architecture. We've got the design coordination to go to do. There's the structural analysis and design, making a building like this stand up very hard. We've got to document it, and we're going to use 3D models, we believed, and we're going to use 2D drawings. So some of these software packages you may be very familiar with. These are the ones that we selected right from the start, and this is which bits of software we were going to use to do which task. But it wasn't really going to work unless we linked it all together with a computational approach. We didn't want to be sucking bits of information manually from one bit of software, putting into another, hope it went in a way that it understood. This had to be far more automated than that. So I want to illustrate the process through the connection elements, the nodes. So this is a sample of what the middle area looks like, and these are some of the elements that come in. It gives you an idea of the form of the elements as they come in, the different shapes, and how many there are. Easily the most challenging part of this project. We had about 300 different ones. The interesting thing is there's no code-based approach for doing this. You cannot go to design code anywhere in the world and find one that tells you how to design that. There isn't a method. And where all the elements intersect, there are really complex stress interactions where all the members converge. What's going on in those areas? We worked out that finite element analysis, which is the highest level analysis that we can do in our industry, was the only viable way that we could actually design these connections. So, but that presented several issues for us. Firstly, our global model, which had all the member forces and moments, etc., took 24 hours to run, approximately, without the nodes in there. So if we want to design one of these nodes, we could create finite elements representation of that, put it in the model, and we'd have to wait 24 hours before we got any results. That was going to be no good to us. We've got 2,500 different types. So we needed to have separate local models that represented the nodes, and we were going to have to map on the results from this big global model. As I mentioned, 2,500 to do. We had 12 months. So we've got to do 50 of these a week. Think about that. Now, Rob and one of his colleagues spent the first 4 months with myself, but they were doing the coding, they were working out how to do this from a computational approach. That means we've now got to do 75 a week. And to put that in perspective, that's 3 during the course of this, during the time of this presentation. So we identified that there were 5 key steps in the process of one of these, design of one of the nodes. The first thing we had to do in this big structure is we had to identify which ones were geometrically similar. We then had to work out what connection methodology might work for that type of node. We then needed to get the forces from the global model for that node and put them on a local model. We then needed to analyse it, work out if the plate sizes we were anticipating and the node configuration that we envisaged would actually work. So there were iterations there to get the node right, and then we had to document it. So identifying the similar connections. So a script was written where we could click on one node, and because everything that's all the properties of the members coming in, the geometry of the members coming in, could be worked out, the script could identify where else in the structure there was a similar node. And I think, well, Rob will tell you more about this if you want to ask any questions, but I think this was probably fundamental to doing everything within the time frame that we had, because we had to automate the similarities. We couldn't afford to interrogate every single node and find which ones were similar. So the next thing we had to do was develop this connection arrangement. What would work for each connection geometry? Now this is pure engineering. There's no computational engineering in this. We had to work out from our engineering knowledge and our gut what we thought would work and how to put these things together. We then built Rhino models. So if you've used the software Rhino, we built a representation of those nodes. There's no point conceiving something if you can't put it together. So the next thing we had to do was do a step-by-step, plate-by-plate fabrication sequence to prove to ourselves that this could actually be made. No point doing it if the fabricator's going to say, I can't actually put this together. It's not possible. And as you can see, this particular one is very, very big. The other thing we had to do was the architect had an envelope for the building, which was the cladding. They had a thickness for the cladding. We had some tolerances. We had some fire protection. And then we get down to the base structure. We had to devise these connections such that they didn't poke out. If they poked out with this complex bounding envelope, it would mean that the cladding would not fit. So we had to prove that that wouldn't happen. And if you look at this as a typical free-form node, this is the kind of connection that we might have put on there. The red is the architectural bounding envelope, and we needed to work out that it didn't poke out. And one interesting thing is that the members coming in are singly curved. The cladding coming in is doubly curved, simply because of the manufacturing processes. And we were able to develop a script where we could alter the depth of this node and look at whether or not it is poking out. Again, completely automated, because we couldn't afford to spend 2 weeks on a node. So with this particular tool, here at 25 mil depth from here to here, it pokes out. Reduce that to 5 mil, it doesn't poke out. We then needed to build this 3D finite element local model. In order to do that, we've got to know the member configuration. We've got to create the surface geometry. we've got to do the fabrication stage arrangement to make sure that it's going to come together and there's no clashes. So all that has to happen before we can do any finite element model. When you do a finite element model of a plate, you've got to model the centre of the plate, not the outer surface, which is what we've already created. So we now need to create the centerline geometry. We've got to apply supports, because in order to analyse them, it's got to have some supports. And we've got to work out how we're going to apply our forces, once we've grabbed them, to this finite element model. Now, in terms of mapping the forces on, as I mentioned, we've got 2,500 nodes in external skeleton. We've got 35 load combinations for each of them. There are up to 9 members in each node. You can start multiplying these and doing the maths. We've got our local model. Because we used Midas for our global model and Midas for our global model and robot for our local model, there's different sign convention in terms of tension is positive in one and it's compression in another. So we needed to flip them. The literally local axis definitions are different. This is just different software working in slightly different sign conventions. The script itself, it actually finds the right forces from the global model. And to show you how difficult that would be, we worked out if we outputted all of the design forces for all of the nodes, for all of the combinations and all of the members on a normal A4 sheet of paper, and we laid them out end to end, they'd reach from London to Paris. So the script has got to be smart enough to work out which ones from all the similar nodes, alter all the sign conventions, and map them all onto our local model in the correct sense, so that if it's in compression, it is in compression, not tension. And as I mentioned, there are literally, I can't remember how many million lines of data. If we printed out everything for the whole model, I think it was 52 million lines. One of the problems of this kind of approach, where you're trying to program something to deal with vast amounts of data, is verification. And we wanted to make sure, excuse me, that we weren't getting it wrong, that somewhere there wasn't some part of the script that was doing it in a way that we didn't intend. So we wanted a visual check on screen. So again, this was built in to the script, where on one side we could have for a node our Midas forces for a particular load case, and we could compare them with what we've got on our local model, which was in robots. And this could be live. You could flick through the load cases and you'd see them changing on both instantaneously. There was obviously, if you analyze from a global model and you extract all the results, they should be in equilibrium. If you apply them to a local model and they're not in equilibrium, there's a problem somewhere. You've gone wrong. So we applied that check, of course. One of the biggest issues about a computational approach, I think, is the criticism that it's a big black box approach, and it could be. The thing about a computational approach, though, is it doesn't allow you to stop engineering. You have to engineer. If you did it by other methods, you need to check. If you do it by computational methods, you need to check. But it's probably easier to build in the checks. But you need to build in those checks. You can't just build a script, press a button, and hope everything is right, because then you are literally dealing with a black box. One of the interesting aspects of this, and I don't know if you've covered this in your course yet, is the interaction of stresses on plates that merge. So, for example, if you take all of these elements, and let's imagine that they're all fully utilised, they're 100% utilised going in, and they've all got 50 thick plates, for argument's sake. When they start interacting, you can't have a 50 thick plate, you're going to need more. And you can do a little test yourself. This is Poisson's ratio effect. So if you compress something, it's going to bulge. It's already going to have tensile stresses in an orthogonal direction. So if you pull it in that direction as well, you're going to get over yield very, very quickly. So we needed to work out that this wasn't going to happen. So analysing all of these models. As I mentioned, we've got so many to do, we've got limited amount of time, and this shows all of the different configurations. Each one is so different from another, and this is a graphical representation of the biggest one probably. It's not the most complex, but it does show you the scale of what we're calling a node. And hopefully from that you will be able to see that you can't really turn to a Eurocode or an American code or any other kind of code to find a methodology on page 5 for how to design these, because it just doesn't exist. Having done all of that, and having verified that the plate thicknesses and the arrangements that we have can satisfactorily carry the load, we then need to document that. It's all very well, we're happy, but we invariably have to prove to third-party assessors of our work that we've got it right and that we haven't made a mistake. So we need to document this, and to a very large degree this was an automated process as well, because we need to do it for all of these nodes. So once we've convinced ourselves that we can do it and the calculations verify that and they can be given to a third party for checking, we've then actually got to communicate the information to the contractor. We chose two approaches here. One was to do the very simple flat connections on conventional 2D drawings, and but the script helped generate these. It didn't do them entirely because there wasn't enough time, but it did help create most of the line work for these. The other approach in the freeform area, if you can imagine something which is really complex and you want to represent them in 2D drawings, well, the first thing you've got to do is almost unwrap it so that people can see what it looks like flat packed. And then you give the information to the contractor and he has to assemble it again. So in a way you've kind of created two tasks that don't need to be done. All you need to do is give the contractor the digital data in a 3D format that he can understand and use for the work that he wants to do. So we spoke with the contractor and we agreed that this is what we do for the more complex areas. If we did this project again, we do it for the simple areas as well. But the 3D model, which we created in Rhino, and for example, every node had a unique reference, every unique reference had its own layer. All the plates that were used in that node were all on separate layers, so they could work out what was 20 mil thick, what was 50 mil thick, what was 100 mil thick, just by their colour references and turning them on and off. It took out the ambiguity from the information that we were giving them. This is one of the flatter parts of the curved central area, and this is a picture of a Rhino model that went on top. Every part of the node that was needed for the contractor to fabricate this node in the way that we intended was given in the 3D model. Just because I think you'd probably like to see what this script looked like. This is the master script, and I think pretty much all of these components are collapsed. They're clustered, which means that if you were to open them up, you would see a lot more inside. And these particular ones here, tin can, which was generally the connection that we used in the freeform area, and 14, which was used on the flat-sided area. This is what's inside the cluster from the main sheet, this one, and this is tin can. So there's a lot of work went into here, a lot of thinking about what we wanted to achieve, and then the tool was a means to an end. There's some very clever thinking that went into it, but it's a means to an end, and that's the thing to bear in your mind when you're thinking about computational approaches to your engineering. Now, I'm going to finish off with a video that kind of summarizes what I've been talking about with City of Dreams, or Morpheus as it's now been renamed. This is one of our younger engineers who worked with Rob on developing this script and making this happen ultimately. So this is his view of this project and what computational engineering brought to the project.
Hi, my name is BuroHappold, and we're coming to you live here at the famous Nuttall strip here in Macau. And today I have a very special site visit I'd like to take you on. It's one of the most unique buildings in the world under construction right now. It's Morpheus Tower, something I've been involved in the design of for the past 3 years. So come on, let's get going. So what is the structural system of Morpheus Tower? Well, as you can see here, we have a steel exoskeleton clad in aluminum. As you can see over here, this is the part of the 42-story atrium, surrounded on each side by a concrete core. Both the concrete core and the steel exoskeleton help support the building in the gravity and lateral cases. And because we're in a typhoon climate, that means that we can have severe forces running through this exoskeleton. So the design of the exoskeleton connections was something unlike anything that we normally see in structural engineering. There's 3 main reasons for that. First of all, we had massive architectural constraints in the form of a 3D polysurface coming from Zaha Hadid that we had to remain inside of. The second one is because of their bespoke nature, every single connection had to have its own way of getting documented. No one's ever seen connections like these before, so how on earth do you document these? But the topic of today's lesson is going to be, how did we do the engineering? The engineering challenges for this project were massive. And remember, on all of this, we had only 12 months to deliver detailed design information for over 2,500 exoskeleton connections. So why was the exoskeleton connection design such a big deal for engineers? It's because all of these members right here are coming together at very complex junctions that no codified approach covers. So right away, codified approaches are out the window. The second thing is we had hundreds of load cases and members that were designed to their plastic capacity and were subjecting the connection to 6 degrees worth of forces and moments. This meant that all the plates in the connection would be subjected to a complex stress state. That can only easily be analyzed via finite element analysis, which of course to me was awesome because I've always been interested in finite element analysis. In a timely fashion, we knew we would need to use a grasshopper-based parametric tool. And that was one of the things that I helped set up at the beginning of the project before using it to create all the connections. The best part about the tool was the fact that it was an extension of the engineer's mind. A lot of the times you see in our industry people making big Excel spreadsheets that make no sense when someone else takes them over. Our design team knew what they were doing because at every stage of the process, it wasn't automation, it was the engineer having his skills be put up in front of him. We saw what we were doing. We knew the forces were being mapped correctly because we saw them. We saw the connections were similar because we saw them. And certainly, we did not let the computer run the finite element analysis for us. We had to check each and every one of those ourselves. So one of the coolest things that I was involved with was doing an experiment after the project was over to show the world exactly how powerful this tool was. So one day I recorded my screen using the grasshopper tool and then also tried to do a bespoke hand calculation for the same connection. And what I found was fascinating. First of all, the grasshopper tool allowed me to perform a higher form of analysis 20 times faster. And because I was using a higher form of analysis in the terms of finite element analysis versus bespoke hand calculations, I was able to effectively save 3 times as much material for the connection. So, what is the future of structural engineering to me? This right here is the future of structural engineering. Us being able to make our own tools to break free of the software constraints that we've become so used to be able to employ our theory on a massive scale. Faster, more sustainable, and also more accurately. This is the future of structural engineering.
Okay, well that gives you a flavour of the work that we've done on this project. We're immensely proud of this project, simply because no one has done a project like this. No one has approached a project like this in the way that we did. And quite frankly, without this project, maybe we wouldn't have started the journey that we are on, But now that we've done it, we are marching forward in all directions. Now that we understand the power of the computer and what computational engineering can do for us and our industry. And Rob is going to show you now some of the cool stuff that he's been up to.
Cool, thanks. That is quite a cool video. First time I've seen that, actually. Yeah, so I'll go over, I guess, a few other, to be honest, quite eclectic examples of computational engineering approach, and in general how we're kind of organising ourselves inside the practice to develop some of this approach. It's really important when you're trying to solve really complex problems to think outside of the box and think outside of even your own industry, and especially outside of the tool set that you've currently got. And you know, some of the things that we have been inspired by computationally are, you know, the likes of Google, who have developed this video is actually from YouTube, a few years old now. They've developed systems that allow cars to be able to see the world in 3 dimensions further and faster than humans can, and in 360 degrees. And so the actual power of the computer is absolutely amazing. And in structural engineering at the moment, we really only harness a fraction of that, even with some of the stuff that we've shown today. As Hayden was saying earlier on in the presentation, it's really super important to reinforce the point that none of this is about getting rid of jobs or the engineer. It's about making the computer do what it should have been doing this whole time that we've been spending a lot of time manually creating models and putting nodes in 3-dimensional space, and let the computer actually get on with that whilst we think and sketch and create, and bring our real structural engineering skills to the fore in terms of sketching different options for solutions, which at the moment the computer is actually not very good at doing at all. So in terms of some of the software that you've seen so far, there are 2 very different families of 3D modelling software. One end of the scale is a vector-based, so points and coordinates and lines and planes, and the other end of the scale is what people keep talking about as BIM, or building information modelling. And building information modelling is a lot heavier, more complex environment where you deal with objects in the computer. So vector-based is lines and points and XYZ coordinates. Object-oriented is a virtual version of a beam and a column, and the models are much bigger and heavier. What we are doing, though, irrespective of those 2 different worlds of modelling in the computer, is employing the same computational approach. So you'll hear parametric design, visual programming, all of which are interoperable with Grasshopper for Rhino and Dynamo for Revit. So these 2 things, Grasshopper and Dynamo, are basically plugins to these 3D softwares that allow you to do some visual programming and control them in an automated fashion. And the reason why we need these 2 worlds is effectively, on the left-hand side, we're very analytical, we're very structural analysis, we're very connection-oriented analysis, and on the right-hand side, we're producing drawings, we're producing huge gigabytes of data to be sent to site for construction. So a sort of practical example that we're working on at the moment that demonstrates not just the structural engineering but other disciplines and a similar approach computationally is Qatar Foundation Stadium that we're working on at the moment. And this is a project that we bid for last year and actually employed similar approaches to what you've seen, not only to be delivering the project now, but to win it in the first place. We had a very small amount of time and fee from a contractor to go away and take somebody else's design that took 7 years and cut the budget by 60% or something like that. So with some of the techniques that you've seen, we were able to cut out 50% of the steel weight of the roof, so saving 6,000 tons of steel. This is a screenshot of the now quite out of date, but structural model for the entire stadium. And what you'll probably hear from other consultants and generally in the industry at the moment is to build an entire model of a stadium in the structure analysis, or indeed City of Dreams. It takes weeks or months of people going in and putting nodes and coordinates in. This model took 3 days to generate, and it took 3 days to generate from an organized system of logic and data that existed on the project. So it does take more time to interrogate and analyze and make sure things are working properly, but these are the kinds of things that we're developing to try and put the analysis and the manual model generation back in its box and let us focus on the engineering. Similarly then to structural engineering, and anyone that's worked with structural packages kind of knows how clunky they are and how bad the user interfaces are. Other disciplines like building physics have similar clunky bits of analysis software. So we're also using a bit of software called IES to analyze the thermal properties of the spaces to define how much energy the building needs to heat it up or keep it cool. And so employing, again, the same kind of processes of taking data, cleaning it up, and putting it into a format that can be put into an analysis model across the different disciplines. These are the two different energy models that we've created. And the process, we did one stadium in the UK, and it took 2 guys 5 weeks. We, on this project, used this new process. It takes 3 hours. So we're talking about 5 weeks worth of somebody fiddling about with nodes down to about 3 hours time. And then in addition to understanding how much energy the building needs to be heated or cooled, we also need to understand, because it's an air-conditioned stadium, what happens when the wind flows over the stadium and sucks out the air-conditioned air out. And so we've also got what's called a computational fluid dynamics model, which models the wind. And these are much more complicated models than your typical structure analysis model. But again, all generated from similar approaches. And so it takes a very small amount of time to generate. To calculate this model, though, it takes 500 cores and produces a results file that's 2.2 terabytes. Which is the biggest, I think, so far that we've produced. So we're dealing with huge amounts of data. Bringing it all the way back then to much more simplistic and early stage design, how can all that kind of amazing computational power and scale and complexity be useful at the early stages of a design? And our CEO always used to come along, and his question was, what happens if I push here on a structure? And the question is meant to basically be answered by saying, well, we need some extra bracing and we haven't really thought about how the building stands up. So it's a question that he used to ask quite often, and it's a good question to ask when you're developing early schemes for a building to make sure you've got structure in the right places. So this is another competition that we won, and then did a short scheme design before it got handed over to a local team in China. It's the new Beijing airport that's under construction at the moment, together with Zaha Hadid, same architect as the City of Dreams project. And you can see this is the main terminal building. It's huge. It's going to double the capacity of Beijing from 80 million passengers to 160. Have I got that right? Anyway, it's huge. And the spans between some of these really complex shape columns are 250 meters. When you're working with architects like Zaha, you need to kind of display and illustrate and explain very quickly the implications of some of these really broad movements that they're making. So we use some of the tools that we've got here to connect Rhino together with robot structure analysis to do a super simple 2D representation of the effect of the bending moments on the structure. When we decided we were deciding with Zaha whether to keep that grid shell in the centre coming down to the support points or to thrust it onto those two side roofs. So these are huge spans, and the bending moments that are coming up are representative, but it gives you a really quick feedback and a way to say to the architect, look, let's not put that grid shell on the side of the roof. It's not a good idea. Similarly then, in terms of, that's just your bending moment diagrams, we can also actually push structures by imposing displacements on them. This was a quick study that we did for a project in the Middle East, where a very kind of seismically biased engineer was adamant that we should disconnect the facade from the building because otherwise it would attract a huge seismic load. And so actually, if you just say, well, let's just push the facade, the exact limit of the seismic code, that the building has to be stiff enough to resist anyway, and see what bending moments are. Is it a problem or is it not? Rather than just simply looking at the code and saying code says no, it's going that extra mile. And so taking those kind of 2D studies and putting them into 3D. I don't know if anyone's familiar with plugins for Grasshopper like Kangaroo to get minimal surfaces. What often doesn't get talked about with these plugins that create minimal surfaces are the real world constraints. So it's quite quick to download this free plugin and create a surface that is very structurally efficient, but who actually has thought about the fact that you need to get a fire truck route through this canopy? And so actually those perfect kind of real world constraints need some input to them to put some realism into the design. And so, developing those free plugins and the early processes and quite quick computational approaches to allow the engineer to interact with that process. And again, this comes back to the whole visualizing and seeing what's going on. So here what we're doing is we're changing the boundary conditions of that freeform analysis, minimal surface analysis, to push it over the fire truck route. And again, more kind of real world constraints being built into these simple study models. On a similar note, then these images are from a project that actually was a competition for the same World Cup as the Qatar Foundation Stadium that we were running at the same time. This was for the roof of the main stadium. We eventually stopped this competition because we won the other stadium. But again, huge value engineering project, taking a huge double layer cable net and trying to make it into a single layer cable net to take the cost out of the roof. And in this case, it's a 250 meter diameter cable net. And we started taking the analysis that we developed for the other stadium and building on it to be able to do this single layer doubly curved cable net. It's really important to note as well that, again, with the plugins that you can download and writing your own kind of scripts to calculate structure, etc., it's really important to benchmark it and check it. And for a cable net, there are some simple checks that you can do by hand, but also it's quite good to benchmark it against always the commercial software that we use. So in this case, we've benchmarked it against GSA and Robot, and the left-hand side is the Grasshopper script that calculates the forces in the cables, etc. So what we're doing here is basically live loading the roof, and we can change the area of the load and the intensity of the load. And what's going on in the background that you'll see in a moment is a Grasshopper script that calculates the equilibrium to calculate what the tension in all the cables is, and then sizes all the cables and gives you then an approximate weight of the roof based on some loading that you've put on. All happening live. This is in real time. And what that does is it gives you a really, really quick feedback of different geometries, and when you pull and push and change the geometry of the ring beam, what effect that has on the structure. Hayden talked a bit about linking one bit of software to another. Huge problem in the industry. All these different bits of clunky software that don't really talk to each other. So, and then there's lots of humans on projects that have biases that like to use different bits of software. Multiply that by 16 firms that are working on a project, and it quickly becomes quite ridiculous. So it's really important, and actually it's a necessity for us to be quite flexible. And so, sort of demonstrating that flexibility on a project in China, where we're working with a local design institute. They work in AutoCAD and their drawings are in Chinese, and they don't know anything about kind of Grasshopper on this project and our kind of processes. So we needed on this project to develop something quite quick that links together the drawings together with the deliverables, because they gave us, believe it or not, 1 week to develop construction loads for the foundations for this bridge. So it's a bridge in Suzhou in China, and the structural system is pretty interesting. It's an eccentric set of box girders separated by this truss in the middle, and so you can do a few handcoats, which is absolutely fine, but when you curve that on plan as well, you start to see some of the complexity of the forces that are acting on the piers, which we had to get a good level of confidence in quite quickly. So this is a screenshot of, or a screen recording of Revit. So this is the kind of building information modeling software. And we basically take the drawings from the local design institute into this and extract from that some guiding curves for the geometry of the bridge. So here we're taking from building information modeling world and very heavy world, extracting some really simple lines and guiding geometry that will eventually then be the basis for us generating the analysis models. That's a screenshot on the right hand side of Dynamo, which is the Grasshopper equivalent to Revit. So Dynamo to Revit is what Grasshopper is to Rhino. And then finally, this is showing that all linking through to the structure analysis. So the input is here, it's 2D AutoCAD, that drives the rules to generate the 3-dimensional sticks for the bridge, and that in turn is exported to the analysis software to get an idea of those eccentric and torsional loads on the piers. A lot of the time in our practice, people say, well, that's fantastic, but my project is really, really simple geometry, so none of this really helps me. But actually, you can use a lot of these techniques on some more kind of repetitive or simple geometry. So on this project, another project in China, in Zhengzhou, we were employed by urban systems architects in London, really, really great architects, to specifically look at the perimeter frame and make it look like it was doing its structural job, including seismic loads and wind loads. So they basically wanted the shape and the size and the spacing of the structure to reflect all the load acting on it, and specifically for us to then develop a Grasshopper plugin for them to look at automatically generating different options for the perimeter frame. So the screenshot on the left is the analysis model. It's showing the stress at the base of the structure at the first iteration. We're now doing seismic, wind and all the other loads acting on the building together and resizing a lot of the perimeter frame based on stress criteria, fairly simple stress criteria, because this is only kind of the preliminary end of the design. What this enabled us to do, though, is there are softwares that will take your entire structure, take all the forces and reduce all of the sizes based on their capacity. But by building your own optimization, you can, for example, say where the structure is really low stress, delete the column, take it out, rerun it, and see what the stiffness is. And also, they wanted us to reverse that process, start with no structure, and actually put it on a predefined grid where the columns and their neighbours were overstressed. So it's by doing your own optimization, you can quite simply put together different rules to see what effect they have on the building. You may not be surprised to learn that the actual result was lots of columns at the base that are quite big and smaller at the top. So then into the detailed design, and actually the example here is City of Dreams, so I won't go into this in too much detail, although you didn't have a screenshot of my favourite analysis model with the curving plates. But it gives you some idea of the complex stress state and the number of different forces acting just on one single node. And that's the same screenshot from earlier. So we have this kind of loose network of individuals around the globe within the company who call themselves the Computational Collective. And so it's a sort of informal group of people who have developed some of these skills around the practice, and we're developing the group a little bit more now to centralise those skills, but also centralise the code. So we've been centralising 35 years worth of code into a nice, clean, new online repository. And what has come out of that sort of computation collective are the idea of a hackathon. So again, learning from Silicon Valley and the tech industry, a hackathon is essentially, although I didn't really know what it was until we kind of had one in Beijing with 6 of us, and it was amazing how much we kind of learned from the process. What I think it essentially is getting everybody together, coming up with a series of example problems or ideas that we want to test or simulate in the computer, and then basically doing it, coding, writing visual programming scripts, taking some example data from a project and doing some different analysis and developing some different solutions. And they've kind of caught on. So we've done quite a lot of these things around the practice. The left-hand side is actually the one that we did in Beijing way back when. And there, within kind of one afternoon, from having no plan whatsoever, coming up with a kind of example problem to solve, we figured out a really nice way to use this cloud service called Flux, which is a Google project, which allows us through the cloud to link lots of different models together. And what we're doing is linking CFD analysis on one computer up through the cloud. Somebody else is doing the structure analysis, somebody else is doing the daylighting, etc. All linked through this Flux service. We actually then extrapolated that and started to partner with Flux, the technology company, and we had a joint hackathon with them between our San Francisco and our London offices. And over 2 days we came up with all these different things that we wanted to try and solve. And it's amazing what you get out of the 2 days of this kind of intensive problem-solving environment. Not to mention all the ideas that people come away with of stuff that we can develop in the future. So again, they've really kind of caught on. Imidio, I think, was the driver of the hackathon that produced this funny shaped skull in the middle, and the intention of the skull was to basically test the limitation of the FE meshing and solving of robot, but also when you watch the video of the kind of session they recorded afterwards, it's got a load of really useful information about the understanding the basics of finite elements and the aspect ratio of the elements and the predictability of the results within those elements. So it's just a bit of a fun way for guys to keep in the discussion the accuracy of all of these models and things that people are generating for buildings. And so that was the different offices as well that we invited to the London and San Francisco hackathon. So we also had a Google Hangout session with people from all these different offices interacting through the Flux server to the same project. Coming back again to the kind of applicability of this stuff to more simple geometry, this is a project that we did in the London office for a modular housing scheme, and the idea here is to develop a structural kit of parts that we know work. They're pre-sized based on a maximum span, etc. And by sketching then in Rhino, the script takes care of the rest of the development of all of the building information model, and it means that you can apply the same modular parts of the structure to different building typologies. And as long as the columns are always at a maximum spacing and the cores are a certain height and aspect ratio, then we know that the structure works because it's been pre-calculated. Moving then kind of more into the experimental and research and development, partly from our sports work and partly from the Computational Collective, we started looking at things like the atmosphere inside stadia and how we can actually start engineering the buildings to improve the atmosphere. So anywhere from how your seating is arranged to the materiality of the roof that reflects sound, because there's a balance between being able to hear emergency announcements, for example, and a crowd getting really excited and cheering really loudly. And so inside this kind of central repository of code, now we have crowd chant propagation plugins that look at, when a chant it starts, how far it propagates based on the loudness and the proximity of the people, and also then taking real data from football matches and mapping that onto the geometry and into the model to start visualizing and analyzing what actually happens in terms of the loudness and the propagation of noise throughout the crowd. So this is when a goal is scored, and you can sort of see all the people jumping up and down and the hotspots of sound. So sort of seems obvious, but what it does is it starts quantifying where that sound is and how well the atmosphere really is contributing to the success of the team. Moving forwards then and into the future, we're moving quite rapidly towards integration of all of the different softwares, but also integration of us into the design and further into the design process, computationally speaking. So on the right hand side is a demonstration video that we put together to basically explain what we're trying to do and what we want to do and what we expect of our software now. So in the first instance, the stick man with the sphere is me being tracked with a 3D depth sensing camera, and I'm walking from Dynamo into robot structure analysis, and then in the third instance I'm walking up onto the cloud service Flux. And so this is a demonstration of really where we want to be with stuff. We don't want to download plugins and convert stuff. We want to be able to seamlessly go between different bits of software. And then on the left-hand side is my colleague Johanna with the virtual reality headset on, because we're now porting a lot of these tools and capabilities into virtual reality so that we can have a more immersive experience in the design. And so coming back to Qatar Foundation Stadium and the CableNet scripts that you saw earlier, we loaded that into the virtual reality space. So my colleague Al Fisher here is inside the stadium. Arnaud is driving the Grasshopper script. And Al Fisher is saying, right, I'm up in the stand and I can't see the ball because that purple line is basically a line of sight where it's saying the roof structure is too low. And so he's moving the roof structure up in virtual reality. What it's doing in the background is it's resizing all of those cables to give you an idea visually of the difference in size of the cables. And then coming back to the computational fluid dynamics analysis that I talked about, we're loading those results into virtual reality because visualizing wind flow inside a stadium is quite a difficult thing to explain. So it's useful then to be able to put a headset on and see exactly what we're talking about. And so it is a bit of a reach to say that what we're doing is kind of similar to Google, but actually, conceptually, it is quite similar. On the City of Dreams project, we're basically teaching Rhino to understand what a structural connection is and to go away and figure out what all the similar ones are. And in the same way, Google cars are learning what human beings look like, and they're actually teaching each other what they look like as well. And we're starting to bring as well, more interaction between ourselves and the actual structure analysis. And so by continually thinking outside the box and learning from the tech sector, we can really push the tools that we've got further and further.
So thank you very much for listening to us. Hopefully you can see that we are in a digital world. Everything that we're doing now is digital, and computational engineering is really transforming the way that we work and the way that we handle data, and creating massive opportunities for us to explore, to research, to improve, and to do things that we didn't even think about doing until we had a project that led us in a certain direction, that led us to another direction. So everything out there is in a state of flux, and hopefully you found this interesting and it sparked your imagination about how you might use computational engineering in your studies and in your future work. So thank you very much.